visual document retrieval has come a long way. From financial reports with complex charts to scientific papers packed with figures and industrial manuals full of diagrams, the ability to quickly find relevant information in these rich visual documents is no longer science fiction. But until recently, the systems that power this capability have been computationally heavy, slow, and expensive. Today, we're diving into a breakthrough paper called NanoVDR, a new framework that distills a massive 2 billion parameter vision language model into a tiny 69 million parameter text-only encoder, while preserving nearly all of the original model's performance. And it does this without requiring a GPU at query time, enabling real-time retrieval on CPUs. So what's the core idea? Let's start with the problem. Most state-of-the-art visual document retrieval, VDR, systems use the same large vision language model, like QN2VL or Polygemma, to encode both the documents and the user's text queries. That means every time someone types a simple question like, "What's the revenue growth for Q2?" the system runs a full 2 billion parameter model to generate a query embedding. This causes massive latency, often over 2 seconds, even for plain text. And it's not just slow. It's inefficient. The model's powerful vision capabilities are completely wasted when processing text-only queries. This design is symmetric, treating documents and queries the same way, but that symmetry is unnecessary. Documents are visually complex, rich in layout, color, and structure. They need strong visual understanding. But queries, they're just short strings of text. No images, no visual content. So why use a heavy vision language model to encode them? That's where NanoVDR comes in. Instead of symmetry, NanoVDR introduces asymmetry, a deliberate decoupling of the two encoding paths. The system uses a frozen 2B VLM teacher to index documents offline, generating single vector embeddings for each page. Then, at inference time, a lightweight text-only student encoder, as small as 69 million parameters, encodes queries on a CPU in under 50 milliseconds. The magic happens during training. The student learns to map text queries into the same embedding space as the teacher, not by mimicking document representations, but by aligning its own query embeddings directly with the teacher's pre-computed query embeddings. This is a key insight, the distillation objective. The researchers systematically tested 6 different training objectives across 3 model backbones and 22 datasets in the VDR benchmark. And they found something surprising. Pointwise cosine alignment, simply minimizing the angular difference between the student's and teacher's query embeddings, consistently outperformed all ranking-based and contrastive alternatives. Why? Because the teacher's embedding space is already well structured. It captures meaningful semantic relationships between documents and queries. So instead of teaching the student to reproduce relative rankings, which requires negative sampling and document embeddings, we just teach it to match the teacher's coordinates directly. This means the training pipeline becomes incredibly efficient. You only need to pre-cache the teacher's query embeddings. No document images, no negative examples, no batch-level similarity computations. The entire training cost for the best NanoVDR model. Under 13 GPU hours, including pre-caching. But here's where things get even more interesting. Even though the student is text-only, it still performs remarkably well. NanoVDRs, based on distills, 69M parameters, achieves 95.1% of the teacher's performance on the VDR benchmark, and outperforms DSEQN2, a 2 billion parameter model on the more challenging V2 and V3 versions. And the efficiency gains. Massive. Query encoding latency, 51 milliseconds on CPU, 50 times faster than DSEQN2. Model size, 274 MB versus 11.9 GB for call poly. Index storage, 8.2 GB per million documents, compared to 264 819 GB for multi-vector systems. Deployment cost, runs entirely on CPU, no GPU required. This makes NanoVDR ideal for edge devices, mobile apps, or low-resource environments where GPU access is limited. Now here's the twist. The biggest performance bottleneck was cross-modal transfer, the mismatch between text and vision, but cross-lingual transfer. The student encoder is based on distills, a model trained primarily on English. When queries come in other languages, French, Spanish, German, Italian, the model struggles to align the embeddings properly. On Portuguese queries, for example, retention dropped to just 75.6%. But the fix is elegant and cheap: multilingual query augmentation. The researchers translated 489,000 English training queries into 5 target languages using lightweight machine translation models. They re-encoded these translated queries with a frozen teacher, creating new target embeddings. Then they combined the original 711K training pairs with 778K translated ones, over 1.4 million total. After retraining, NanoVDRs Multi, the multilingual version, saw a dramatic improvement. Retention jumped from 92.4% to 95.1%, and Portuguese queries improved by 9.3 points. This proves the bottleneck is language, not modality. And it can be solved with query-only data augmentation. No need to reprocess documents or re-encode images. So what's the takeaway? NanoVDR shows that asymmetric distillation, using a powerful vision language model only for document indexing, and distilling its knowledge into a tiny text-only encoder, is not only feasible, but superior in practice. The key design choices. Use pointwise cosine alignment as the distillation objective, simple, efficient, and highly effective. Exploit the query-centric nature of the training to enable cheap, scalable multilingual augmentation. Leverage the single-vector structure of the teacher model to inherit storage and retrieval efficiency. In the end, NanoVDR's multi-69M parameters matches the quality of a 2 billion parameter VLM, runs 50 times faster on CPU, and trains in under 13 GPU hours. It's not just a technical achievement, it's a paradigm shift in how we think about efficient visual document retrieval. And this isn't just about speed. It's about accessibility. It's about making powerful multimodal retrieval available to everyone, not just those with access to high-end GPUs. So the next time you're searching for a specific chart in a financial report or a diagram in a scientific paper, imagine a system that answers in less than half a second on your laptop with no GPU required. That's the future NanoVDR is helping us build.